Hi students, hope you all are fine. So we'll continue the chapter electric charge and fields. Last class, let me quickly revise what we have discussed. So I told you that if you have a body and if it loses its electrons or if it gains new electrons, then it gets charged. If it loses electrons, it becomes positively charged, and if it gains electrons, it becomes negatively charged. And we discussed the methods of charging. There is charging by contact and there is charging by non-contact. The charging by non-contact is called induction. Then we discussed about the properties of charge. One of the property of charge is any charge q, okay, that you measure is always equal to some integer times e, where e represents the magnitude of charge of electron, whose value we write 1.6 into 10 to the power minus 19 Coulomb. And if you gain electrons, the charge will be negative. If you lose electrons, the charge will be positive. Okay, so this is called quantization of charge. Then the second property we discussed was if you have a system, okay, which is isolated. Isolated means there should be no interaction between this system and the surrounding. So if the surrounding does not interact with the system, then whatever is the total charge inside the system, the total charge of isolated system, that will remain conserved, or we can say constant, and that we call conservation of charge. The third property, I think this third property I mentioned in the first, right? And that is called additivity of charge. Additivity of charge. What it basically says is charge is a scalar quantity. Meaning, if a system has charges Q1, Q2, then the total charge of the system is given by algebraic sum of the charges which are within the system. So these are the three properties of charge which we discussed: quantization of charge, the conservation of charge, and additivity of charge. Then I told you that, I think in the last part, I told you that if you have a charged body, positively charged body, then it can attract negatively charged body, no doubt, but it can also attract neutral bodies. Neutral bodies. How is it possible? The reason is this positive charge, whatever negative charges are there, will be slightly attracted this side. So this side will become negative and therefore the far side will become positive. Now this negative is nearer to the positive, so attraction will be more than the repulsion, right? See, this negative is attracted by this positive, but this positive will be repelled by this positive. But this attraction will be more simply because the negative charge is nearer to this positive charge. So overall, the neutral body will be attracted. Same thing will happen with minus charge, right? If this is negative, then it will attract positive body, or if it is negative, then what will happen? It will repel the negative charges that side in the body. So this will become minus now, and this will become plus. Even now you can see the plus charge is nearer to this negative body. So this negative body will attract the neutral body. So overall the point is, if a charged body attracts another body, then that another body can be either oppositely charged or it can be neutral. Okay. Uh, so this is something I want you to know. This is called polarization. This separation of positive and negative charges in the body is called polarization. So today we are going to, I think we started with entrance corner, right? We were supposed to start the entrance corner. So today we'll complete entrance corner of the first session, and then we'll continue with the remaining syllabus. So entrance corner 1. So first question says, which of the statement is incorrect? Which is the incorrect statement? So first statement, option A, charge is either positive or negative, but mass is always positive. That is correct, right? Mass is always positive. Charge can be positive or it can be negative. Option B says, charge of a body is independent of its velocity, but mass of the body depends on its velocity. So if you have a body which has charge q, okay, and if it starts moving with some velocity v, then also its charge remains q. That means charge is invariant. Charge is invariant under motion, meaning whether a charge is at rest or it is moving, the value of the charge will not change. This is not the case with mass. So if you have a body which has mass m, okay, at rest, and if that same body starts moving with some velocity v, then from Einstein's special theory of relativity, which is not taught in pre-university, not in class 11 and 12, but it is taught in degree, okay, BSc. There you will learn his theory of relativity, and there you will learn that if a body is moving with a certain velocity, its mass will actually increase. So the mass which it will have now, let us call it m dash, will be equal to this mass which it had when it was at rest, divided by root over 1 minus v square by c square. Okay, so v is the velocity of that body and c is the speed of the light. C is speed of light. Now, usually in day-to-day life situations, the velocity of the body will be much smaller than the speed of light. Even if you consider jet planes and all, which can travel with speed of sound, 330 meters per second, quite fast. But compared to speed of light, which is 3 into 10 to the power 8 meters per second, speed of that body will be very small. 330 is negligible compared to 3 into 10 to the power 8 meters per second, right? And on top of that, if v is less than c, v square will be even smaller than c square. Yes or no? See, 2 is less than 5. But if you square both the sides, 4 will be much smaller than 25. So v square will be very small. So this is a very small number. You are dividing by a large number. So if you divide small number by large number, the ratio will be extremely small. So 1 minus extremely small will be roughly 1. So this will be roughly 1 in daily life situations where the speed of the body is much smaller compared to the speed of light. So then in that case, the mass of the body while it is moving is same as mass of the body while it is at rest. That's why when we do Newton's mechanics, we consider the mass of the body to be constant. We consider the mass of the body does not change with velocity. But in fact, the mass of the body does increase when the body moves. Yes, in normal situations, we can ignore that. But but there are some particles, right? In cyclotrons, which you will be studying in second PU, there is a device called cyclotron where particles can be made to move very fast. So in such cases, the increase in the mass due to its motion has to be considered. So option B is also correct, because in option B they say charge of the body is independent of velocity, but mass of the body depends on the velocity, as we have seen. Third option says when a neutral body gets positively charged, its mass slightly increases. So if you have a neutral body, neither it is positively charged nor it is negatively charged. Now if it gets positively charged, how will it get positively charged? If it loses its electrons. If it loses its electrons. Now you know each electron has a small mass 9.1 into 10 power minus 31 kg. So if it loses its particles, its mass will obviously decrease. Maybe slightly, but it will decrease. So first option says mass will increase, but it actually decreases. So option C is incorrect, which means you should tick option C. Option D says when a neutral body gets negatively charged, if you have a neutral body and it gets negatively charged, that means it is gaining electrons. If it gains electrons, then it's getting new particles. If you get new particles, the mass of that body will slightly increase. But here in the option, they said mass will slightly decrease. So option D is also incorrect, so you have to tick. Okay? So that completes question number 1. Let us see question number 2. A conductor has a charge plus 1 nanocoulomb. Then the number of electrons added or removed from the conductor. So since the body has plus charge, it is very clear that you have to remove electrons, right? So second question is, the charge in the body is given plus 1 nanocoulomb. So how many electrons should be removed? So to calculate the number of electrons which should be removed, we will use quantization of charge. Q is equals to Ne. So number of electrons will be equal to charge divided by E. The given charge is 1 nanocoulomb, which means 10 to the power minus 9 coulomb. Charge of electron in magnitude is 1.6 into 10 to the power minus 19 coulomb. Coulomb will cancel. This will be 1 divided by 1.6 into 10 to the power minus 19 will go up plus 19. Plus 19 minus 9 will be plus 10. And if you do this calculation, 1 divided by 1.6, you get 0.625 into 10 to the power 10, which can be written as 6.25 into 10 to the power 9 or 11. If this number has increased, this number should decrease, so it should be 9. So this many electrons should be removed. So which is the correct option? Option D. Okay. Let's see the third question. A positively charged body attracts. Option A, negatively charged body only. Yes, a positively charged body will attract negatively charged body, but only we cannot say, because you know a charged body can also attract neutral body, right? So option A is not correct. Option B, positively charged body attracts positively charged body. That is obviously false. Option C, neutral body, yes, correct, but only they have told. So that we cannot take. And the last option is it can attract, positively charged body can attract both negatively charged body as well as neutral body. So option D is correct. So third question we have already discussed. Question number 4. Okay, this is important, okay? It is slightly tricky also. So here it says 5 balls are numbered 1 to 5. So there are 5 balls which are numbered 1, 2, 3, 4, 5. And they are checked pair-wise. How they are checking? Whether those 2 balls in that pair are attracting or repelling. So they are saying pairs 1, 2, 2, 4 and 4, 1. These pairs are shows electrostatic attraction. So they show attraction. Now that means what? That means if this is plus, this can be either minus or it can be neutral. Yes or no? We have discussed that. And similarly, if this is minus, this can be either plus or it can be neutral. Then they are saying pairs 2, 3 and 4, 5, they show repulsion. Okay. If they show repulsion, then it means these bodies are pakka 100% they are charged. CHARG, they are charged, right? Because if you show neutral body will never be repelled by a charged body, remember. So this pair and this pair are showing repulsion. So these 4 balls are 100% charged. Question is we have to find ball 1. Is it positively charged or negatively charged or is it neutral? This first ball that we have to find. So let us try to understand. See, These four are 100% charge, we came to know, because they show repulsion. Here they showed 2 and 4. These 2 and 4, they show attraction. That means if one is plus, other one is minus. So we came to know ball number 2 and ball number 4 are oppositely charged. Plus or it can be minus. 1 we don't know the charge, okay, 1. But we know 2 and 4 are charged and they are oppositely charged. Now this one, they said, is attracted to this ball, and the same ball is also attracted to this one. Now that means, see, if this is positive, how this positive will be attracted to this, and if this is negative, how it will be attracted to this. So this clearly means that this must be neutral. Only if it is neutral, then it can be attracted by plus body also and negatively charged body also. So that shows ball 1 is neutral. Okay, so it's an interesting question. So which is the right answer? Option C. The fifth question says, an electron moves along a metal tube with a variable cross section. How will its velocity change when it approaches the neck of the tube? When it approaches the neck of the tube. Okay. So they are saying there is a tube which has a variable cross section. So this area is changing. Okay. And from here one electron is moving with some velocity. As it reaches the neck of the tube here, neck of the tube here, what happens to its velocity, they are asking. Will it increase, decrease, or remain constant? Whatever may be the velocity. Now you know, since this is metal, as negatively charged moves, these free electrons will be repelled, right? This negative charge will repel the free electrons to the far side. So far side will be negative. And therefore this side will must become positive. Right? Because it will have deficiency of electrons. All the electrons went to one end, so this near end will be oppositely charged, positive. So as this minus charge comes nearer to this plus will attract it this way, and this plus will attract it this way. Yes or no? So the electron will feel force this way and this way. So resultant force will be where? According to parallelogram law, resultant force will be here. Okay, so as the electron moves with velocity v and approaches this neck, okay, that time the resultant force will be in this direction, same as its velocity, which means velocity will increase, isn't it? If you are running this side and I push you in the same direction, you will move faster than before, or at least you will fall down faster. Okay. Whereas see, when it was here, that will not happen, because this positive will attract this way, this positive will attract this way, so these two will cancel. Only when it approaches the neck, then the forces will be this way. Okay, one force will be here, one force will be here, so resultant force will be there. It will not be zero like in this case. So velocity of the velocity of the electron will increase. The right option is here. It is given B, whereas it should be A. Okay, so you can please do the correction. Velocity has to increase. So now we will continue the next session, which is session 2. Okay, so in session 2 we have Coulomb's law, its vector form, and superposition principle, very important, and force due to multiple charges, which is actually superposition principle. So let us start with Coulomb's law. Coulomb's law. Okay. So if you remember, when we did gravitation chapter in first PU, there we studied that if you have 2 point masses, okay, they will attract each other with a force which is given by what formula? G m1 m2 by r square. Right? In the same way, there is a law called Coulomb's law that tells us what would be the force between 2 point charges. The first thing to understand is Coulomb's law holds for first point charges. Okay, so do not apply it for other kind of charges like spherical charge or ring of charge. For those we will see what to do. But right now, to apply Coulomb's law, the charges must be point charges. And those charges whichever you have taken must be at rest. Okay, so these are the two conditions or two limitations of Coulomb's law. Okay, fine. Now let us say we have two charges, and the symbol for charges we usually write Q. So I have two point charges. One is Q1, other one is Q2. And if the product of the charges is positive, then it means what? If one is plus, other is also plus. If one is minus, other is also minus. Then it means they will repel each other with some force. Okay, and if the magnitude of the force is F, this force magnitude will also be F. Newton's third law says, right, every action should have equal and opposite reaction. So if this magnitude is F, this will be also F. If I write vector F bar, then I will put minus, right? But I am not writing vector symbol, right? So it means magnitude will be same. Now if this distance is R, then according to Coulomb's law, the statement is the magnitude of the electrostatic force. The magnitude of the electrostatic force between two point charges is directly proportional to the magnitude of the charges. Only the magnitude. Do not worry about the sign. Okay. Divided by, and it is inversely proportional, which means I have to write divided by square of the distance between the charges. Square of the distance between the charges. And it also says the force will always be acting along the line joining the charges. So if one charge is here, one charge is here, then the force will always act along this line. Okay, if both are positive, it will be like this, repulsive. And if one is positive, other one is negative, then it will be attractive. But it will be always along the line joining the point charges, which is a property of what kind of force, if you remember? A force which obeys such a property is called central force. Okay, central force. So it's good to know that electrostatic force is a central force. Anyways, so coming back to Coulomb's law. So this is the statement. Okay, so I hope, this is the expression statement you can see in the notes. Okay. Now, if I write a constant, if I write equal to, then some constant will come, proportionality constant. We write that as K. And I will write Q1, Q2. Okay, I will not write mod. Modulus I will not write. So please understand these two are magnitude of the charges, because we are writing the magnitude of the force divided by distance square. Which distance? Distance between the charges. So this is your Coulomb's law in mathematical form. Now this K plays the role of this capital G. However, there is a small difference. This capital G does not depend on the medium between the masses. So if you have two masses M1, M2, and if you put in the medium water or whatever, Coca-Cola or Fanta, it doesn't matter. The force between the masses remains same. That is because this capital G is a universal constant. Whereas this K, the value of this K depends on medium between the charges, whatever medium is here. Okay, so that you have to remember. And of course, it also depends on the system of units. System of units. That is obvious, right? Because it will have some unit. What will be the unit of this K? The unit of this K, which is called Coulomb's constant. This K is called Coulomb's constant. Okay, what will be the unit of this K? Cross multiply. So F R square. F will be Newton. Cross multiply. R square will be meter square. Then this Q1, Q2 will come downstairs. So it will become Coulomb, Coulomb, Coulomb square. So that is the unit. So if you change the unit, the value will also change, right? My height may be 1.3 meter, but in centimeter it will be 130 centimeter. So the number will change if you change the unit. Okay. So this is what is K. Okay. Now there is one interesting detail about this K, Coulomb's constant. Okay. So if you remember, the constant capital G in this formula was measured by Cavendish. Okay, Cavendish, and we have that topic in first PU chapter, gravitation chapter. Okay, one of the first PU chapters, gravitation. So there we have done the theory behind the experiment which was performed by Cavendish to measure the value of capital G. Same experiment we can repeat with charges instead of masses, and then we can measure the value of K, this Coulomb's constant. Okay, so that the theory behind the experiment is not there for us to do in the syllabus, but whatever was done there, you same thing you repeat it. So whatever value was found, now I told you this K depends in medium, right? So in vacuum, if you measure the value of this K, it comes out 9 into 10 to the power 9. How much? 9 into 10 to the power 9. And the unit we have discussed, right? Newton meter square divided by Coulomb square, which I can write per Coulomb square. Okay. Now, this is the value of K in vacuum. If you repeat this experiment in air, you will get roughly the same answer. Okay, so in vacuum or in air, the value of K is taken to be same. It will be slightly different, but for at least our purpose, we can take it to be same. Now, uh, in Coulomb's law, how did we write? K Q1 Q2 by R square. Yes or no? However, the way we write this K is not simply the constant we don't write simply K. What we do is we write this K as 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Okay. So that will be your 9 into 10 to the power 9. So this K, so the way Coulomb's law we write in vacuum is instead of writing K, we write 1 by 4 pi epsilon naught. Now, of course, you are dying to know why we are doing like this, right? This looks more simpler than this, right? Then why are we making it more complicated? That's the first question. And second question is, what is this epsilon naught? See, whatever may be this epsilon naught, you can calculate the value because we already know the value of K, which is this much, right? The experiment we can do. So from the experiment, we know the value of K is this much in vacuum or in air. So once we decide that, we can write K this way, and once we write K this way, what will be epsilon naught? Cross multiply. So it will be 1 divided by 4 pi into 9 into 10 to the power 9. Okay, and this if you measure, if you calculate this, it will come 8.85 into 10 to the power minus 12. Okay, and what will be the unit of this epsilon naught? Well, see, K contains epsilon naught in the denominator. So whatever is the unit of K, ulta will be the unit of epsilon naught, ulta reciprocal. So this means the unit of this epsilon naught will be ulta. If you do, this will become per Newton per meter square, and per Coulomb square will become Coulomb square. Okay, so this is the value of epsilon naught. Now I'm saying epsilon, epsilon, right? Epsilon is the name given to this Greek alphabet. Just like this is A, this is B, this is C, right? This is a Greek alphabet whose name is epsilon. But here we have to give it a name for our purpose, right? So the name given to this epsilon naught is permittivity. Permittivity. And this naught represents it is permittivity of which medium? Vacuum. Or we sometimes call it free space. Free space. Okay. So keep in mind the value of this epsilon naught. Okay, so now let us discuss quickly why are we doing this, because I was little bit upset when my teacher wrote such a simple formula this way. This doesn't look very beautiful, right? And I always believe physics equations are always about to make it look beautiful. By beautiful I mean it should be compact, but it should be able to explain many things. Okay, so why is it Why are we making it more descriptive than compact? Well, the answer of this took a lot of time for me to find. Okay, but that is the beauty of teaching, right? Whatever I gain knowledge through my studies or research, which I take months or sometimes even years, my students will get it in few minutes. So that is how knowledge accumulates. That is how mankind gets developed in the uh, knowledge knowledge side. Okay, so the reason why we write this case this way is, later as you will do more topics in this chapter, as we will do more topics in this chapter, you will come to know that we need to multiply this quantity with area of spheres. Area of spheres. Okay. So this sphere will keep coming, a lot of spheres will be discussing later. And when the area of the sphere will come, we will need to multiply this quantity with area of the sphere, which is how much, if you know, 4 pi r square. And that time, this 4 pi and this 4 pi will cancel, and then the result will look more better than this one. Okay, then if you don't write this as 1 by 4 pi epsilon naught. So if you keep it as k, then when you multiply with area of sphere, your 4 pi r square will, this 4 pi will get stuck. But if you write this k as 1 by 4 pi epsilon naught, and later when you will multiply with the area, another law will come. Very soon we will be discussing that law. That law will look much simpler if you write this constant as 1 by 4 pi epsilon naught. So that was a historical reason for writing the k this way. Fine? Okay. So once we have learned how to write Coulomb's law in vacuum, let us say in medium what will happen. Okay. Okay, let me just quickly discuss. So in medium, the force between two charges, let us write Fm. Okay. Between two charges, we write 1 by 4 pi. Here we wrote before epsilon naught, which was representing what? Permittivity of vacuum. Now we will write only epsilon, Q1, Q2 by R square. And what will be this epsilon called? Before it was called permittivity of vacuum. Now we will call it permittivity of medium. Which medium? Whichever is present in between the charges. Okay. So this formula is used when you have two charges Q1, Q2, and the whole medium is filled with another, the whole space is filled with another medium. It is no longer vacuum or air, and that medium will have some permittivity, which we write epsilon. Of course, if you think, what will happen if only this much is filled with medium, not the remaining part, then the things become more complicated, and that we will discuss for entrance. Okay, so let us continue. Now, if you take permittivity of medium and you divide it by permittivity of vacuum, then this we called, see, whenever you divide, if you take density of any object and you divide it by density of water, water is a standard kind of standard substance, right? Everywhere is available. Then whatever density comes, whatever ratio comes, what do we call it? Relative density. Similarly, if you take permittivity of medium and divide by permittivity of vacuum, we call it relative permittivity. We write it as epsilon r. So this is called relative permittivity of medium, whichever medium is present. Okay, so please remember epsilon can be written now as epsilon naught into epsilon r. Okay, next chapter where we will do capacitors. Okay, there we will also there we will give another name to this epsilon r. Here we are calling it relative permittivity. Another name for it is dielectric constant. Dielectric constant of the medium. Okay, and that time we usually write K symbol. So dielectric constant K is same as relative permittivity, which is epsilon r. So if you see this, then I can now write force between uh, two charges at some distance. In medium I can write now epsilon, I can write epsilon naught into epsilon r. Yes or no? Epsilon into epsilon naught into epsilon r. Now if you see this part, what was this? Try to think. This is nothing but force in vacuum, which we wrote F. So force in medium is nothing but force in vacuum divided by epsilon r. So very useful relation. Try to remember it. So either you call it relative permittivity or you call dielectric constant. Now for insulators, this epsilon r is greater than 1. For example, for water, the value of this epsilon r is 80. Obviously, it will not have unit because we are dividing epsilon by epsilon naught. So it's a ratio of same quantity, so units will cancel. That means what? If the force in vacuum is 160 and I put water, then the force in medium will be how much? 160 divided by relative permittivity of water is 80. So it will become just 2 Newton. So a strong force can be reduced by putting water between the charges. That's why Na plus and Cl minus in your sodium chloride crystal, when you put water, it dissolves because the attractive force becomes weak. Okay, and that's why we say water is a good solvent. Okay, so try to remember this result. Okay, so once we have understood, okay, that how to write magnitude of force between two point charges. Again, I'm saying point charges. Now let us learn about vector form. So next topic is vector form of Coulomb's law. Vector form of Coulomb's law. Okay. So we will try to represent the same force but in vector form. So before I start this, let us revise some few things about vectors. Okay. Some of you may have forgotten it, so let me quickly revise, especially the concept of unit vector. So imagine you have this green vector which I call A bar. Okay, then the magnitude of this green vector, magnitude means how much, right? So if I apply a force of like this 10 Newton, then 10 Newton is the magnitude. Where I'm applying gives you the direction. So when we represent a vector by this arrow, it means what? The length of the arrow gives you the magnitude. And wherever the arrow points, that gives you direction. Okay. So let us say the magnitude which we write like this, modulus of A bar, or sometimes we simply write A. Let us say magnitude of this vector is 10 units. The exact unit will be decided by this quantity. If it is force, it will be Newton. If this is velocity, this unit will be meter per second. Okay. Anyways, now if I divide this vector whose length represents the magnitude, which I have taken how much? 10 unit. Then I can imagine this vector to be divided into 10 parts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Now tell me what will be the length of this small vector here. The length of this small teeny weeny vector will be 1 unit, and a vector whose magnitude is 1 unit, whose length is 1 unit is called unit vector. So this is a unit vector which I can represent by a cap or any letter, but put a cap. Now can I say this whole vector a bar is equal to a cap? Can I say? See, their directions are same. A cap is here, A bar is also here. But can I say they are equal vectors? No, because their direction may be same, their magnitudes are not same. This is 1 unit, this is 10 units in my example. In my example, I took magnitude of this how much? 10 units. So they are not equal. But if I write 10 times A cap, right? A cap, A cap, A cap, A cap, 10 times if I do, then I will get my this original vector, A bar. So A bar is 10 times A cap, which now I can write. What was 10? Magnitude of A bar, so I can write mod of A bar A cap. So this way I can write A cap as A bar divided by mod of A bar. So keep this part in your memory. because this has been already done in first view. Okay, so now coming to the vector form. See, there are two ways to do it. One is one very simple way, and one is the one that actually you should study for your board exams, because that is how NCERT has done. Okay, so let's say I have two charges Q1, Q2. Okay, let me write Q2 here. Now let me choose origin. Now origin, where you can choose origin, you can choose wherever you want. So let us choose origin wherever Q1 is. So this is X axis, this is Y axis. So this I have chosen as my origin. Then if you draw a vector from origin to any point, then that vector is called position vector. So right now, what is this position vector giving you? It is giving you position of this charge with respect to this charge, and the length of that vector will give you the distance between the charges. Okay, and in the direction of this r bar, let us assume there is a unit vector r cap. Then since r cap is along this vector r bar, I can write r cap as r bar by mod of r bar from this concept, which means I can write r cap as simply r bar divided by r. What is r? Magnitude of r bar, which means distance between the charges. Now coming to the force. The force on this charge by this charge. See, force is always calculated on a body by a body. Okay, it cannot be such a force on nothing by something. So force on Q2 by Q1. Let us assume the product of the charges is positive. Okay, so if this is plus, this is also plus. Then the force will be repulsive. So force on Q2 by Q1 will be along this line, and it will be repulsive. So it will be like this, F21 bar. And force on Q1 charge by Q2 charge will be repulsive. Like charges will repel, and it will be along this line. Let me write this as F12 bar. Okay, so once I learn how to write the vectors, how will I write in mathematical form? So F2 F21 bar will be modulus of the vector times unit vector in this direction, right? A cap should be in the direction of A bar, A cap. So which unit vector I have chosen along this vector? See, this vector is in this direction, and already I have written r cap in this direction, right? So I can simply write r cap. Then force on charge Q2 by charge Q1 will be, magnitude is given by Coulomb's law, 1 by 4 pi epsilon naught. In vacuum we are doing, okay? Q1 Q2 divided by r square r cap. So this is your vector form in Coulomb's law. You can massage this equation more. You can write r cap as r bar by r. So you can write r cap as r bar by r. Right, and r square into r will become what? R cube. So this is a nice way of representing Coulomb's law in vector form. What about if I want force on 1 by 2, charge q1, force on this charge by this charge? It is this vector. Now how will you write this vector? Same way, magnitude times unit vector in this direction. But already I have shown r cap in this direction, but I want unit vector in this direction. What should I do? Flip it. If you flip a unit vector, it will become negative, right? In first PU, we have learned about negative vectors. So if this is A bar, what is this? Minus A bar, okay? So this is r cap. I want unit vector in this direction now. So just flip r cap. So if you flip r cap, it will become minus r cap. Then magnitude is same only, 1 by 4 pi epsilon naught Q1 Q2 by r square r cap, and minus sign I can write here. Okay, so now if you see these two equations, this one and this one, you can easily judge that F21 bar is minus of F12 bar, which means Coulomb's law obeys Newton's third law. Action and reaction are equal, but minus sign means they are opposite. Now, though this is a very easy way to do, and this is the way actually if you do it, it is much better. But in NCERT, what they have done is they have taken the origin not at the location of one of the charge. Okay, I have chosen origin at the location of one of the charge. So let us see how NCERT has done. So you have this charge Q1 and you have this charge Q2. They have not chosen origin here. They have chosen origin somewhere else. So here they have chosen. So in that case, what will happen? This Q1 will have some position vector. Let us call this R1 bar. Okay, let me write it more nicely. So this vector will be position vector of charge Q1. Similarly, this charge will have a position vector R2 bar. Okay, but I want distance between them, right? So I want position of Q2 with respect to Q1. So I want this vector. Let us call this vector R bar for the time being. Now look carefully. From triangle law, you know that two vectors which are taken in the same order, if you add, you will get the third side which is in the reverse order. This is in the reverse order, right? These two are in the same order. This is in the reverse order. So if you apply triangle law, you know that this R1 bar plus this R bar must be equal to this R2 bar. So what is R bar? R2 bar minus R1 bar. Okay, so let us write this somewhere. R bar is R2 bar minus R1 bar. Fine. Okay. Now let us talk about the force, because ultimately we want to write Coulomb's law in vector form. So force on Q2 by Q1 will be along this line. Let us again take the product to be positive. So the force will be repulsive. So this will be your F21 bar and this will be your F12 bar. Let us choose along R bar like we did before, unit vector R cap. This is R cap, okay, unit vector. So how will you write F21 bar now? Like we did before, magnitude into unit vector in this direction, which is R cap. Now what will be this magnitude? We know from Coulomb's law, 1 by 4 pi epsilon naught Q1 Q2 by distance between them means length of this vector, and length means what? Modulus of the vector. So modulus of vector square into R cap. Now before I simply wrote R square, it's the same thing, but now let me write it as modulus because I want to bring R1 bar and R2 bar. Now what is R bar? R2 bar minus R1 bar. So let us substitute. So 1 by 4 pi epsilon naught Q1 Q2, and this I can write modulus of R2 bar minus R1 bar square into R cap. How can I write? R cap is unit vector in the direction of this R bar also, right? So I can write R bar by mod of R bar, which is R2 bar minus R1 bar divided by mod of R2 bar minus R1 bar. If I substitute this here, it will become R2 bar minus R1 bar divided by mod of R2 bar minus R1 bar. So if you see the denominator, this is R2 bar minus R1 bar modulus square. This is R2 bar minus R1 bar modulus. So this will become cube, right? So this will become cube. And this you can put in brackets. So this is the way to write Coulomb's law in vector form. Okay. Similarly, if I write now force on 1 Q1 by Q2, this force, then I will put minus R cap, minus, minus, minus. Okay, so that is how we can write Coulomb's law in vector form. Students, the next topic which I am going to deal now is very, very, very important. Okay, based on that, you can do problems which are there in NCERT for board syllabus, but also you can deal with mini entrance level problems. So that principle is very powerful. We call it superposition principle. See, whenever such principle comes, right, principle, law of conservation of momentum, law of conservation of mechanical energy, so such principles are going to be your tools to solve a new problem. So whenever such principles are taught, please keep in your mind very deeply and try to remember it. And whenever a new problem comes and you get little confused, think whether you can apply these laws and these principles. So what this principle says is, see, if you have two charges, Q1, Q2, and you want to find the force on this by this, then we can write Coulomb's law, right? We have just learned. But what if there is another charge? Then what should we do? So if there is another charge Q3, then what shall we do? Then we will apply superposition principle, which says, let me tell the statement, okay? So if there are multiple point charges in a system, and you want to find force on one of the charge, then what you have to do? Find the force on one of the charge by all the other charges, okay, taking one at a time, and then take the vector sum of those forces to find the resultant force. So that is the idea behind superposition principle. So if imagine you have been given three charges like this, Q1, Q2, Q3, and I want force on this charge, then what you do is, imagine Q3 is not there. Find force on Q2 by Q1 using Coulomb's law. So it will be along this direction. If I take both are positive, let's say this is negative, okay, for change, okay. So if both are positive, it will be repulsive. So force on Q2 will be this way by Q1. Let us call this F21 bar. So that is the force on Q2 by Q1. And that force is independent of whether this is there or this is not there. Very important. A question in CET, it has been asked. They told two charges Q1, Q2 are present. Force on this by this is F. Another charge is kept here. What will be the force on this by this? It will remain F only. Okay? See, I am not saying this will feel the same force. Once Q3 will come, then Q3 will also apply force on Q2. So resultant force on this will change. Resultant force will change, no doubt. But force on Q2 by Q1, that will remain 1 by 4 pi epsilon naught Q1 Q2 by R square. That will not change whether another charge is there or not there. And that's why superposition principle is valid. Okay. So first what you do, if you want to find the net force on Q2, first find force on Q2 by Q. Then find force on Q2 by this minus Q3. Imagine Q1 is not there. It will be along this line. And it is minus, this is plus, it will attract. Okay, so this force is F23 bar. Then the resultant force, okay, resultant force on Q2 will be given by whom? By not Q1, by Q1 and minus Q3 will be given by vector sum of this force by Q1 plus this force which is by minus Q3. So it is vector sum, remember. So it is important that you revise vector sum in first PU. Okay, let me just quickly remind you. If two vectors A bar and B bar are given to you at angle theta, then the resultant will be along this diagonal R bar. So your R bar will be A bar plus B bar. And if you want to know the magnitude of R bar, magnitude means again, either you put modulus or you simply write R. That is given by root over A square plus B square plus 2AB cos of angle between A bar and B bar, which I wrote theta. What will happen if the vectors are in the same direction? A bar and B bar are in same direction. Then your theta will be 0 degree. Put 0 degree. Cos 0 will be what? 1. Then this is A square plus B square plus 2AB, which is A plus B whole square. and that root over whole square will give you a plus b. So if the vectors are in same direction, then the magnitude of the resultant is simply the sum of the magnitudes of the two forces or two vectors. Okay, but otherwise you don't do. Suppose I say 3 Newton and 4 Newton are added. What is the resultant force? You cannot say 7 Newton without checking the direction. If they are in same direction, then you can say 7 Newton, 3 plus 4. But if they make angle 30 degrees, then you have to use this formula. Okay, please keep this in mind. What if they're in opposite direction? Then what is the angle between them? 180. And here cos was there, right? So cos 180 is minus 1. So this will become minus. And this is formula of a minus b whole square. Root is there. So root of a minus b whole square will be a minus b. So all these things you should revise, which is taught in vectors. So this is your superposition principle. Okay. You can add one more charge. Let us do here. First you make a note of this. Okay. Now suppose I add one more charge here. Q4. Then what will I do? Then Q2 will feel a repulsive force from Q4. That will be F24. Okay. So you have to add these three vectors. To add three vectors, usually the trick is first you add two vectors. So this is the resultant force F bar which I wrote. Then you have to add this one with this one. Okay. So this is your F24 and this is your F bar. So how to add? Make a parallelogram. Okay, so this will be the resultant force. Whatever symbol you add, Fr, let's say. Okay, so this is the resultant of these two, which I wrote here. Then if you add one more force, you have to add with the resultant of these two, this third force. Okay, that will give you the final resultant force on this charge. Okay. Now, doing this way will be very tricky, right? Because you need to keep finding the angles. So the best way in such cases is take components of the individual forces. Okay, so take components along x-axis and y-axis. Once you do that, find the x component of the resultant force by adding them or subtracting depending on whether they are in same direction or opposite direction. Find the x component of the force, find the y component of the force, then find the resultant by using root over x component square plus y component square. So even this is taught in first PU vector algebra. Okay. So this is the whole idea behind superposition principle. Okay. So once we have learned this, I would like to show you some few problems. Okay. So that is under entrance topic. Whenever I do entrance topic, I will put hashtag. So whatever follows now, okay, till I tell, that will be for only for your entrance purpose. So let's say I have a triangle and in the corners of the triangle I put three charges Q, 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 and the side of the triangle is B. My question is find force on one of the charge. Magnitude only I want. Then what to do? Use superposition principle. Find force on this by this. Both all are plus, okay? So force on this by this will be repulsive along this line. Let us call that F. What will be the magnitude? 1 by 4 pi epsilon naught in vacuum only. Q, Q, both are Q, Q divided by distance between them. How much I wrote D? D square. Right? Now, this charge will also feel force because of this charge. So they are also like charges and this is the line joining them. So force will be repulsive along this line. Now, will this force have same magnitude? Yes, because this product of charges is same as this product of charges. And this distance is same as this distance. So the magnitude will be same. Direction obviously will not be same. Now, we have to add these two forces. So what is the angle between them? 60 degree. Why? But this is 60 degree. Why? Because it is equilateral triangle. So resultant force will be root of f square plus f square plus 2ff cos of 60. Cos 60 is half. So if you put here half, 2 and 2 will cancel. This will be f square. F square plus f square plus f square will be root 3 f square, which will be simply root 3 f. Right? And f we have already calculated. I mean, we have already found 1 by 4 pi epsilon naught q into q square. This is q square divided by d square. So that is the answer. Direction will be where? Direction will be along the diagonal. And since these two are equal, it means this resultant will bisect this angle. Okay? If you have two vectors like this, then the resultant is here, right? And if the magnitudes of these two are equal, then this resultant will bisect the angle between A and B. If A is larger and B is shorter, then you can say resultant will not bisect. Resultant will be closer to this vector. But if the vectors which you are adding have same magnitude, then resultant will bisect the angle. So this is the first exercise. Let us now see second exercise. We'll make it slightly more complex. So let's say I give you a square this time. Okay, here charge q, here charge q, here also q, and here also q. All are like charges. Distance is again d, let's say. The side of the square is d. I want you to find force on this charge or any one charge. It will come same. So force on this charge by this charge, repulsive, right? So F here. Okay, remember, okay, it's always along the line joining the charges. F. And what will be that F? 1 by 4 pi epsilon naught q square by distance d square. Force on this by this, same or different? Same, because charges are same, distance is also same, right? D here, D here. So this force will be along this line, repulsive. F. But now we have another charge here, q. So it will be along the line joining the charges. That will be also repulsive, it will be here. Now tell me, will this have same magnitude? No, because this distance is more than this distance. So force will be less, F dash let us say. And what will be F dash? 1 by 4 pi epsilon naught q, which is q square, divided by this distance. Now if this is d, this is d. What is this distance? Pythagoras theorem says root of d square plus d square, which is root 2d. So this distance is root 2d. So here root 2d square we have to do, root 2d whole square. That will be simply 2d square. Okay. Now if you look carefully, this is your f only, right? Here. So I can write f dash is f by 2. So this is, now I have come to know this is f by 2. Let me write here itself. Now we have to add these three forces. Do not add these two first. If you add these two first, resultant will be somewhere here, right? So then you have to find that vector and this vector angle. No need to do that. Best way is add these two. So these two are making, so first add this f and this f. So what's the angle? 90 degree. So resultant will be in this direction. That will be root of f square plus f square. No need to write 2f cos 90 because cos 90 is 0. So this will be root 2f. Okay, and since these two forces are same in magnitude, the resultant of these two will bisect the angle. If it bisects the angle, it means what? It means this resultant of these two will be in the same direction as this force, because this force is along this diagonal. Understood? So now we have to add this force f by 2, the third one, with the resultant of these two, which is how much? In the same direction. How much? Root 2f. And these two forces are in same direction. So to find the resultant, just add these two. F by 2 plus root 2f. So the resultant force which we want will be 1 by 2 plus root 2, and f you can take common. Once you take f common, what is f? This is f, right? So 1 by 4 pi epsilon naught q square by d square. So this will be your answer. Okay. So let us continue. It's quite interesting to do more and more exercises, right? See, when you do more exercise, what happens is whatever you learn, the ideas that you learn, the concepts that you learn, it sinks. Okay, it sinks in your brain. It stays in your brain for longer time. So it's always better that you solve more and more problems. So let's take third example. So here I am going to give you some symmetrical distribution of charge like before, but question will be slightly different. So here is charge Q, here is charge Q, here is charge Q, and along the not along sorry at the centroid here I keep another charge Q naught. Okay, my question is what is the force on this Q naught? And the answer is force on Q naught by these three charges, that will be 0. That's because of symmetry, but let us understand why. See here, all are like charges. Okay, so this Q naught will be repelled by this Q. So the force is F, let's say, along this line. This Q naught will be repelled by this Q along this line, right? And magnitude will be same because this distance, if I say R, then this is also R, this is also R. And force on this Q naught by this Q will be repulsive. So these three forces we have to add. Now, what is this angle? This is 120, this is 120, this is 120, right? So these two forces, F and F, okay, this F and this F are at an angle of 120. So resultant of these two will be root over F square plus F square plus 2 into F into cos 120. Cos 120 degree is minus half. Okay, cos 180 minus 60, cos 180 minus 60 minus cos 60, minus cos 60 minus half. If you substitute minus half, 2 and 2 will cancel, this will be minus f square. So root over f square plus f square minus f square. F square minus f square cancel. So what is left? F. Beautiful. That means if two vectors having same magnitude are at an angle of 120, the resultant will be also having same magnitude. Keep this in your mind. So these two, when you add, resultant will be along the diagonal, right? Which means it will bisect this angle because these two are having same magnitude. So resultant will be here, which will be also F. And that F, you have to add with this third one. So the third one is sitting here. Resultant of these two is also F. And it will bisect this angle 120. So it must be exactly here. So you have to add with this one. And these two are in what direction? Opposite direction. And the magnitudes are same. So resultant force on this Q naught. This is resultant of only these two. I want resultant of all the three forces. So that will come out this F minus this F. Why minus? In 180 degree, right? I've already explained. So that will be 0. Okay. So that's nice. So you have understood that the charge Q naught which was kept at the centroid will experience 0 net force because all the other charges were identical. Let's say the same thing. Suppose we have a square. Here we have Q, here we have Q, here we have Q, here we have Q. And at the center, I keep a charge Q naught. What will be the force on Q naught? Can you tell me quickly? Answer is 0. Okay, why? Again, simple. So this one is more easy than previous one, right? So this Q naught will be repelled by this Q, F. This Q naught will be repelled by this Q, F. Magnitude will be same because product of the charges is same, remember. Distance is also same. So this F will cancel this F. Similarly, the force on this by this will be here, and force on this by this will be here, and that will also cancel. Okay. So now if I ask you, suppose I give you a regular pentagon, okay, or let's say hexagon, and if I keep the charges in the corners and I ask you a charge on this, force on this charge, again you can say 0, provided charges everywhere are same. Okay, you need symmetrical. Okay, so if this is q, this should be q. If this is minus q and this is also minus q, then also the force will be 0, right? Because this will be attracted to this minus q and this will be attracted, so forces will be equal and opposite. Suppose I give you a pentagon now. Okay, so again I am drawing hexagon only, right? Am I drawing hexagon or pentagon? This is hexagon only, right? So let me try to draw a pentagon. Pentagon has how many sides? 5 sides, right? So let's say something like this. Okay, yeah. Okay. So here if I put, it's difficult to show the uh, slightly difficult to draw it actually. Okay, so if you have a pentagon and if you keep charge at the center, okay, something like this. Yeah. So if I keep charge here at the center, Q naught, and I put here Q, 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 Q like that, and I ask what is the force on this. By the same reasoning, you can say force on this will be 0 because of the symmetry of the distribution of charge. Okay, I have not drawn a perfect pentagon, but I hope you got the point. So such problems, you should not waste time solving it in your entrance exam. Immediately see the option, see the question, see whether there is symmetry or not, then the net force on that charge at the center will be 0. Okay, so let us now continue with the exercises in our EPR. So we have numerical exercise 1. Okay, so we'll start solving numerical exercise 1. So the first question says 2-point charges 100 microcoulomb and 10 microcoulomb are separated by a distance r in air. Exert a force of 25 Newton. So let's say one charge is Q1, 100 microcoulomb. Second charge is 10 microcoulomb. Distance between them is r, which we have to find. And they exert a force of 25 Newton in air. Okay, so if they say air, then we can use permittivity of vacuum. And they are saying what is the force between them. First we have to find the distance r. Okay, find r. Then they are saying what is the force between them when the space between the charges is filled with oil of dielectric constant 3. Dielectric constant means epsilon r, which is relative permittivity. Also we write K, capital K. Okay, small k was your Coulomb's constant. So it's a direct problem based on Coulomb's law, right? R they are asking, force they have given. So what is the formula for force? 1 by 4 pi epsilon naught Q1 Q2 by R square. What is the force given? 25. And this is nothing but your small k, right? And the value of this small k was how much? 9 into 10 to the power 9. That you have to memorize, okay? They will not give you in question paper. So the value of this constant in air or vacuum is 9 into 10 to the power 9. Q1 value is how much? 100 microcoulomb. Matlab 10 power minus 6. Q2 is 10 microcoulomb. 10 into 10 to the power minus 6 divided by R square. So 25 equals to, this will be 9 minus 6 minus 6 minus 12 minus 11 minus 10 minus 9, and the 10 power minus 9 and 10 power plus 9 will cancel. So 9 divided by R square. So R square will be 9 divided by 25. So R will be square root of this, that will be 3 by 5, which is 0.6 meters. Then they are asking what will be the force when the space between them is filled with oil. Now if you put a dielectric medium, matlab insulating medium between the charges, then the force in medium, if you remember the formula, is force in vacuum divided by epsilon r. Force in vacuum they told 25 Newton, or in air the same thing, okay, and epsilon r is how much? 3. Okay, so this is 3 8s are 24, 1 carry, 3 and Newton. So that is the force in your uh, oil, medium oil. Okay. Okay, so now we have already discussed for 1 hour 15 minutes. The remaining time, as I have told you in the last video, the remaining 15 minutes I will be using to solve doubts which are asked by students, and it will help all of you. Okay, so that's why I'm keeping 15 minutes for doubt clarifications. So remaining problems, numericals, we'll do in the next video. Okay, so the question that is asked. Okay, so I should find some, no, I write it DC. Okay, so when I write DC, it means I'm clearing doubts, doubt clarification, clarification. See, this is wasting time on you in spelling and all. So doubt clarification. So the doubt has been asked by one of my student. Okay, his name is Rohan. Rohan, I hope you don't mind telling your name. It's actually good. Okay, that I'm mentioning your name so that others will also learn and ask doubts. So the doubt is like this. There is a YouTube, okay, not the one you're watching, okay. It's a manometer basically. It's a YouTube and it contains a liquid in the two arms. And those two arms are at different temperatures. The arm here is at temperature T1, this is at temperature T2. Okay, is it visible? T2, this is T1. The liquid column here has height L1 from the bottom, and the liquid column here has height L2 from the bottom. So this is the liquid. They are asking you to find coefficient of volume expansion, which we write gamma. So this question is based on two chapters actually. One is mechanical properties of fluids and one is thermal properties of matter in first PU. Now the first confusing thing is how come the column here is higher than column here? Because usually if you have a manometer, okay, if you have a manometer like this and you pour water, then in equilibrium the level of water here and here must be same, right? It would be very surprising if this level is less and this level is more, or like this. It's very surprising. So why the level will be same? See, for that the system should be in equilibrium. I don't want the system to accelerate. So if the system is in equilibrium, then it means the liquid is not sloshing back and forth. So then it means the pressure here and the pressure here must be same. If the pressure here is more, then the liquid will flow this way from high pressure to low pressure. If the pressure here is more, liquid will flow this way from high pressure to low pressure. Right? And what is the formula for pressure at the bottom of a column? P. Pressure at the top, which is atmospheric pressure, because this is open to atmosphere. This is also open to atmosphere. So pressure at the bottom is pressure at the top plus rho g h. Rho is the density, g is the acceleration due to gravity, and h is the height of this column. Now you know that this p should be same here also, here also. But in order for p to be same, this thing should be same. And P naught is same, density of water here is also same, here is also same, right? G is also same, both are on earth only, right? So H must be same. So matlab whatever height here it has, here also it should have same height. That's why this question is interesting, because here the height is more than here. That is because the temperatures here and here are different. And when you change temperature, density gets affected. And if density changes, to keep the pressure same, height also has to change. Height also has to change. So first what you have to do is you have to learn the relation between density at a given temperature with density at another temperature. So let's say I have certain mass at temperature 0 degrees Celsius, and that time the volume is V naught and density is rho naught. And what will be rho naught? Mass divided by volume. Okay, so these are volume and density at 0 degrees Celsius. Now let me increase the temperature to T degrees Celsius. What will happen? It will expand. Yes or no? Usually things expand when you heat, unless you worry about water during 0 to 4 degrees Celsius. So neglect that part. Okay, it is not mentioned here, right? This is not ice. So when you increase the temperature, volume will increase, but the mass has to be same, right? When you heat something, you are not putting matter there. You are not taking matter out. You are just heating. You are just putting energy. Okay. So the mass will not change. So mass will be same, but volume has become more. So let us call the volume Vt. Then density will also change. So density will be mass divided by the new volume. New volume is Vt. Now, how to relate this volume with this volume? You know from thermal properties of metal, change in volume is gamma into original volume into change in temperature. Delta T we used to write, right? So delta V is change in volume. So from here to here, what is the change in volume? Vt minus V naught. Gamma is called coefficient of volume expansion. V is what? Original volume, which is V naught I wrote. And delta T is the change in temperature from 0 degree to T degree. So it will be T minus 0. Now if I take V naught that side, I can take V naught that side and take that V naught common. So I will get 1 plus gamma T. So this is how volume at T degrees Celsius is related to volume at 0 degrees Celsius. So from here, what will be your density at T degrees Celsius? Density at T degrees Celsius will be mass divided by volume at T degrees Celsius, which is Vt, which is this. So V naught 1 plus gamma T. But what is mass divided by volume at 0 degrees Celsius? That is density at 0 degrees Celsius. So I can write this as density at 0 degrees Celsius divided by 1 plus gamma T. So try to remember this relation, that density at T degrees Celsius is density at 0 degree divided by 1 plus gamma T. Okay, so this much concept should be known to us. Once we know this, okay, I've already taught all this in first year actually. So once you know this, okay, then you can easily solve this problem. See, you know that this system is in equilibrium. Okay, so that means the pressure at this point should be same as at this point. Okay, let us call this point 1, this is point 2. So P at 1 should be same as P at 2. Now P at 1 will be what? Pressure at the top, atmospheric pressure, plus rho. But rho at what temperature? T2. So let's write rho T2 into G. G doesn't depend on temperature, into this height, which is L2, equal to pressure at the bottom here, P2. That will be pressure at the top is also atmospheric because both are open to atmosphere. P naught plus rho at temperature T1, remember. This part is at what temperature? T1. G L2. Then P naught will cancel, right? Bring it this side. Then, and what is this density at T degrees Celsius? Density at 0 degrees Celsius, 1 plus gamma into temperature, which is T2. G will also cancel, no need to write. L2 equal to this one, same thing I can write. Density at 0 degree, 1 plus gamma T1, G cancels, L2. Now this also gets cancelled. No, this is, okay, this is L2, this is L1. This is L1. Okay, I wrote here 1, here 2. Okay, actually for keeping the, the way I'm writing, to keep it similar side, this is 2, this is 1. That doesn't matter actually. Same thing, right? Okay. So this is L1. So now rho naught gets cancelled. Then you cross multiply. L2 into 1 plus gamma T1 equal to L1 into 1 plus gamma T2. Then you open L2 plus L2 gamma T1, L1 plus L1 gamma T2. Which is more? L1 is more. So let us take L2 that side and bring this on this side. So if you do that, let me clear this space. So if you bring this one this side, you will get L2 gamma T1 minus L1 gamma T2 equals to, take L2 that side, L1 minus L2, then gamma, take gamma common, will be L1 minus L2 divided by L2 T1 minus L1 T2. So that will be the right answer, because I have expressed gamma in terms of whatever is given, right? Okay. So besides doing this problem, let me also tell you the answer of the question which I asked in the last class. Okay. So in the last video, I told you that charge is obviously a fundamental quantity, right? Charge is conserved. Conserved quantities are obviously fundamental. In current is basically charge flowing per second. So that looks to be derived. But in first PU, when we mention what are the fundamental quantities or units, we write current as fundamental, right? And not charge. So why is that so? I asked. Well, the answer is this. In physics, we have many quantities. And we have the option to choose certain quantities as fundamental. And those quantities should not depend on each other. Okay, they are fundamental. And other quantities should be derived from those base quantities or fundamental quantities. So that option we have with us. We can choose. For example, most of you, we say current is charge by time, right? So we feel like charge is fundamental and current is derived. Yes, but somebody can always say, that, sir, why can't I write the same equation this way? Is this wrong? This is also correct. So then I can say current is fundamental and charge is derived. Understood? So we have the option. The only thing is these two should be independent of each other. Then this can be derived. Or these two should be independent of each other and this can be derived from these two. So these two are fundamental here. And here these two are fundamental. So which option, that is up to us only, right? But what physicists do is whichever quantity can be measured with more precision, that quantity we will keep it as fundamental, because we want to measure it more precisely. And currents can be measured more precisely than charge. And that's the reason why current has been taken as fundamental. Okay, so instead, in fact, in NEET and JE also, they ask questions like, Planck's constant h, speed of light c, gravitational constant capital G. So take these three as fundamental, they will say, and uh, find the relation for the derived quantity mass in terms of these fundamental quantities. So they will consider mass as derived from these three, and then ask you the relation. So in that case, what we do usually, we write this mass proportional to some power x, some power y here, some power z. And then we write the dimensions and we solve the equations by equating the powers. Then whatever equations we get, we solve, and then we get x, y, and z. Okay, so there is no rule as such that these are the quantities which must be taken as fundamental. We have the option to choose a certain set of quantities to be fundamental, then other quantities will be derived from those fundamental quantities. And we want those quantities to be fundamental, which can be measured with more precision. And that's the reason why current has been taken fundamental. So remaining, I think first question we have solved in numerical exercise 1. Remaining we'll be doing in the next video. Okay, thank you.